Hello, students. Today we're going to learn about shaft components. There are many factors that affect the way that we design shafts. Things as the material that we select to make the shaft, the geometric layout of the shaft, and the types of components and changes in diameter that are necessary, the static strength of the material, the fatigue resistance of the material, but also things such as deflection and rigidity of the shaft. How much bending or torsional deflection we can expect in the shaft, and how that affects the alignment of bearings and support elements. And then finally, the vibration of the shaft. Since shafts are rotating members and they're subject to loads that can be dynamic, the question becomes, are there certain critical frequencies of the shaft that if we spin our part at that, if we spin the part near that frequency, could energy build up in the part and we have failure due to hitting or sitting on one of those critical frequencies, or even transitioning through a critical frequency as we spin our shaft up or down. Now, shafts tend to be fairly complex structures. They have various shoulders and changes in dimensions. There may be gears, there may be bearings, a system of bearings on them in order for them to function. There's two aspects that we have to think about in terms of shaft. We should think about stress, which is primarily something that is localized at critical regions, where our shear forces and bending moments are highest, but also where we have things like stress concentrators, changes in dimensions, and sharp geometric transitions. On the other hand, deflections are global. The overall way that the shaft is loaded and supported affects the global deflection and change of shape of our shaft, which can affect its function. Now, materials. Typically, shafts are made of low carbon, cold drawn or hot rolled steels, and 1020 to 1050 type steels. So these are not very, very expensive, high alloy content steels. And the fatigue properties of shafts usually don't benefit much from high alloy content or additional complex heat treatments. Generally, the only hardening that is done to these steels is where they are in contact with other features, such as bearing surfaces. And overall, a shaft should be ground finished and polished precisely so that all the parts, the gears, the bearings, can be mounted, can have tight dimensional mounting along the shaft. Now, a primary purpose of a shaft is to transmit power. So this here is just an illustration of a transmission box where we have one shaft, which has a worm gear, and that worm gear is used to transmit power into another shaft, which is perpendicular to the first shaft. We can see that there's a couple of features in this transmission box. First of all, the box is enclosed, and the box is filled in an oil reservoir in order to keep these gears lubricated to prevent wear and fretage fatigue of the gear teeth. We also can see that we have tapered bearings at both ends of this transmission box, which act as thrust bearings. So if there is any axial loads transmitted down the shafts, this bearing keeps the shaft in position. These sets of bearings carry that load and keep the shaft perfectly aligned for the transmission of power. We'll also note that the design of this transmission box is symmetric so that we can prevent any types of bending moments that might be transmitted through the structure. We want balanced moments being transmitted through these bearing mounts. Now, the layout of shaft designs, issues to consider for shaft layout is the axial layout of the components, how they are spaced and aligned along the shaft, how we support axial loads that are transmitted along the shaft, how we are transmitting torque, transmitting power from the shaft into other components, and then also can we actually assemble and disassemble our shaft? So if we have, say, a bearing that wears out, we can replace it. Or if a gear wears out, how do we disassemble and replace that component? Now, in terms of um, the axial layout very much depends on the scenario of your design. In some cases, your design will just focus on transmitting power through a series of gears. In some cases, you may have a design that has a belt that is transmitting power into your shaft in order to turn a fan. Um, and then there are various situations where you may need thrust bearings or just your typical linear bearings in order to allow your shaft to rotate. Some of the best practices in designing shafts is to support load carrying components between bearings so that you have points where those moments can be equally distributed between more than one bearing. Try to only use two bearings in most cases. Rather than over constraining and applying too many bearings, which can have an effect on deflection, it's best to try to limit the number of bearings. Keep the shaft short to minimize bending and deflection. A long shaft is going to deflect more than a short shaft. And then consider the alignment and load balance within your structure to minimize vibrations. The better that the support loads are distributed more equally, the better outcomes in terms of the minimization of vibrations and friction on at one location over another of support in your shaft. Now, torque transmission. How do we transmit torque? Which is in essence, remember the calculation we make for power, right? Where power is equal to torque times angular speed, right? Or angular velocity. How do we transmit that torque from one shaft to another? There are many different types of features that we can introduce in order to transmit torque. Keys and splines, set screws and pins are very common, but we also have things like tolerance rings and shrink fits and tapered fits. Keys are one of the most effective. They're a slip fit of the component onto shafts for easy assembly. They have a positive angular orientation of the component, and we can design keys to be the weakest link. The key can be the weakest link to failure in case of overload because of their dimension and size. So a better way to think of shafts before we get more into detail on keys and splines and pins is in designing shafts, we can think of them in two ways. We can think of the one-off shaft, where we're making a one-of-a-kind part to a very low production part. In those cases where there's only one that we're making, often we don't want to invest a lot of money into making unique tooling and custom castings because the cost would be too high. So often one-off shafts or low production shafts are not highly optimized. Instead, the shafts are, made of commercially available components. We use standard links, bearings, and gears. We go to handbooks for shaft sizes and use standard sizes. And keys are often used for the transmission of torque from one shaft to another. However, when we are producing mass production shafts, when we expect to produce many thousands of units, it can be worth it to invest in a unique, one-of-a-kind shaft design. Whether that shaft design is stepped, where we change the diameter from section to section, or even whether it's actually tapered, functionally tapered over its length. Mass-produced shafts can have custom components that optimize the displacement and stresses that are transferred through the shafts, and often splines are used in order to transfer loads and torques effectively. So now let's get into a couple of the components that we see in shafts, common types of components. Set screws. Set screws are fairly common. Set screws on a shaft are used to resist axial and rotational motion. They apply a compressive force to the surface of the shaft to create friction. The tip of the set screw may also slightly penetrate, so actually dig in to the shaft. And various different types of tips are available for the set screw, whether it's flat or cup-shaped, oval, sharp cone, or even a half dog. These are all different ways to induce friction in the surface of the shaft and be able to kind of, resist axial and rotational motion and set a position of a component such as a gear. Now, keys and pins. Keys and pins, those are tools used to transmit torque from one shaft to another. So let's consider that we have a shaft of a larger dimension and we have a shaft of a smaller dimension. To interface them and to transmit torque between them, we introduce a key or a pin which interconnects both of those shafts and over which shear stress develops, direct shear develops in the transmission of that torque, right? Based on that, idea, then the key often becomes the region of failure because has a very small cross-sectional area, where the pin as well becomes a region of potential area, critical region. So generally, what do we have? We have a shaft. We, are transitioning from one component to another. We drill a hole, and then we place a pin to connect this shaft to that shaft. Press the pin through. The pin is long enough to span both the outer shaft and the smaller shaft, and now we've got the transmission of torque. Similarly for keys, you've got your larger shaft and you've got your smaller shaft, and you introduce a key, a slotted key, that is then able to slide in and easily then assemble to transmit torque between these two shafts. Now finally, let's talk about the Woodruff key. This is one of the most useful key designs, where rather than having just a straight up rectangular key, instead we have a semicircular key. What is the benefit of having a semicircular key? Well, the key fits into a circular recess in the shaft and a matching slot in the mating part. The beauty of the keys is that they're self-aligning due to their curved shape. They prevent both axial motion and ensure torque transmission, so they're commonly used in automotive and machine tool applications. Some of the gifts of keys. They're easy, of Woodruff keys. They're easy to install and remove. They act to reduce the stress concentration because rather than having sharp corners, they have a continuous curved surface. And so they're ideal for high-speed applications. Now, finally, let's talk about splines. Splines are fairly complex structures used to transmit torque. So they're often used in mass-produced shafts rather than one-offs. Splines are ridges or teeth on a shaft that mesh with grooves in a mating part, like a gear or a hub structure. They're used to transmit torque while allowing for axial motion down the axes. This series of basically teeth increase the surface area over which the torsional shear stresses are distributed, making this a very, very ideal and damage tolerant way to transmit torque, where if one of these teeth become damaged, you still have a bunch of others to carry the load. Applications, they're found in gearboxes, drive shafts, found in aerospace component and precise machinery. And the main advantages, high torque transmission capacity because of the large surface area, precise alignment because of their dimensionality, and they can accommodate axial motion. So if there is an expectation of some axial motion in a structure, it allows for that type of motion between two shafts, some tolerance of spacing between two shafts. With that said, we've covered most of the basic components for shafts. Now, there are more complex shaft components out there, but we'll look to the textbook to learn more about those.